Hi everybody, Mr. D here. Just checking in with a video from IBSL2 paper. It's basically a calculus-based question. Here it is, number 13a. We're given an exponential function with a higher degree exponent. So let's look at part A. We're given points labeled on the graph, and we're asked to identify the 2 points of inflection. And then parts B, find the first derivative. Second, show that second derivative is equal to this expression. C, find the x-coordinate of each point of inflection. And D, use the second derivative to show that one of these points is a point of inflection. So let's start with part A. The point of inflection is basically where a function changes concavity. So in other words, colloquially, is when it basically goes from smiley face to frowny face, or frowny face to smiley face. So in other words, in this area here, this looks like it's half of a smile. So that's concave up. And then at B, changes concavity. So the function is concave down. That's like your frowny face. And then here looks like half of a smiley face. So that's concave up. So changes in concavity occur at B and D. And those are 2 marks. So you get 1 mark for each of those in the mark scheme. Part B is find the first derivative of the given function. And then part 2 is show that the second derivative is this. So that's basically a question you would do using differential rules. So away we go. So here's my response to part A, basically illustrating what I just indicated verbally. First derivative, well, in this case here, you can see that we have an exponential function. So the derivative of any exponential function is in fact that exponential function and any chain rule that may result from the exponent. And there you have it. So as I mentioned earlier, the actual exponential function times the chain rule. So there, I just rewrote it in a different sequence because multiplication can be rearranged. Order doesn't matter. 2 times 3, for example, is equal to 3 times 2. So we use the chain rule there. And then we have to take the derivative of this first derivative to come up with the second derivative. So we have a function that looks like is basically broken up into 2 sub-functions. So what basically we need to do there is use the product rule. So that the 2 functions would be basically this one here. That would be one of the functions. And then the other function would be basically this function here. So you take the derivative of the first function, which is -2, and you multiply it by the second as it is. Add the derivative of the second function multiplied by the first function as it is. And then you basically just collect like terms or factor. Either would apply here. Common factor, the e to the negative x squared. Because it's a show that question, we know that we need the e to the negative x squared. So we're going to common factor that. So you get a -2 from this term, a -2x multiplied by -2x from the second term. And the plus is carried through. And then we just do a little housekeeping and rearrange the addition so that way it looks more like the show that we were asked for. And that's as required. 13C, on the other hand, was what are the points of inflection? Well, now that we have the second derivative, courtesy of the prior part, we basically take the second derivative and equate it to 0 and see if we can solve that equation. But in this case here, we have a fairly complex equation that could be done using algebra, but we have access to the GDC. So I'm just giving you some sort of GDC breakdowns. You would enter the function, the second derivative function, and y equal, and then go to second calc 0. So if you're keen on seeing that, you basically go to y equals e to the negative x squared times 4x squared minus 2. And much like you would have on an exam, you may have functions from prior questions that you may not care to delete. So I'm just going to go ahead and deselect those by hitting enter, and then select the one I'm interested in, hit enter. Make sure there aren't any others that are selected, because I've been doing a collection of these videos. Obviously, many of you would have seen some of them and recognize some of those functions from prior questions. So I'm not too keen on deleting them right away. So I'm going to go to my Zoom standard, which is a good place to start, and then have a look at the function. Well, we want to know when the function, in this case here, the second derivative, is equal to 0. I can't quite make out exactly what's going on. So let's try a Zoom fit now that we've done the Zoom standard. See if that's any help. It may not be. We'll see. Well, there you have it. So let's see if we can find where these zeros are. We can also zoom in a little more so. It looks like it may be asymptotal on either end. But if you're not totally sure, you could basically do a zoom box. So you can go zoom, zoom box, enter, and then move your cursor to the area of the function that you want to investigate. So I'm going to go up. It looks like a symmetrical function, so why don't we, symmetrical about the y-axis that is, so why don't we start our box here, hit enter, move up across the x-axis, and then move across basically to the x-axis, or the y-axis, excuse me, and let's see if we can in fact discern what's happening in that area. Well, it looks like, in fact, as I suspected, we do have a firm 0 here, intersection with the x-axis. So that's what we're looking for. When is the second derivative equal to 0? So we're going to go to second calc, excuse me, and look for the 0. We're going to scroll along until the cursor becomes visible. Let's see if in fact my y values are x values increasing or decreasing. Looks like my x values are getting closer to 0, so I should be seeing the cursor at some, there it is. Oop, a little too far. So we're going to go the lower bound, or left bound is to the left of the 0. Go down one more, hit enter, and there is our 0. So I could quite easily just sort of take a picture of that and embed it as in my file if I wish. And paste that there. And it looks like I've already gone ahead and done that. So I got the negative 0.7071. And if I did the same process, if I didn't recognize that there was symmetry about the y-axis, I would have done the same thing on the right-hand side. But there was in fact symmetry. That would save you some time. So moving ahead now. Part D was use the second derivative to show one of the points above is a point of inflection. Points of inflection are where concavity changes. So we could use a sign diagram of the second derivative to show that there's a change in concavity. So here's our sign diagram. We know where the zeros are. In other words, where the second derivative equals 0. We just did that in part C. So we can show the change in concavity either to the left of this 0 and to the right of that 0, or you could pick the positive one and use a test point on either side. I chose, just for simplicity purposes, to use the positive value instead of dealing with a negative test point to the left of this particular 0. So what's the easiest or most intuitive test point to use in this region? I would say 0. And to the right of 0.7, I would argue 1. So those are the two test points I in fact use, and it's important to substitute them into the second derivative because we have to use the second derivative to show the change in concavity. So here we go. Do a quick substitution. And what we're interested in is not so much the actual value, but whether it's more like its gender or the sign of that result. And here we have a -2, which indicates we have a negative second derivative at 0. And if to the right it becomes a positive, then we know of a change in concavity. And sure enough, we have a positive value multiplied by another positive value. You can use your GDC to prove it's greater than 0 if you're not totally sure. So we have concave down and concave up. And therefore, at x equals this particular value, there is a point of inflection. And that's what we were required to do. Hope you enjoyed that video. If you have any questions, send them my way. I'll do my best to provide full solutions.